Hey guys, in this video we're going to be talking about the Bohr model. So at the end of this video you should be able to describe the tenets of the Bohr model and the experiments that led to the development of the Bohr model, which we kind of already talked about already, but we're going to expand upon that, and then recall what the principal quantum number is and how it is related to the Bohr model. So last time we left on the idea of the line spectrum. So we were like, okay, there's this line spectrum, and we don't actually know where it comes from. Well, it's Bohr, Niels Bohr. So Niels Bohr was the person who explained where the line spectrum came from. Okay, so prior to what I'm about to explain, let's think about what was occurring. So we had Rutherford, and he had what's called the orbital description of an atom. So prior to this, Rutherford had an orbital description of an atom. Okay, where the electrons orbit the nucleus. And this did not explain the line spectra. So electrons orbit the nucleus. Did not explain line spectra. However, Bohr adopted the idea that electrons within the atom are quantized, and he came up with his Bohr model. So he described the electrons' energies as quantized. And then he developed his model for the hydrogen atom. Okay, so within our Bohr model, we are going to describe orbits for our electrons that are going to correspond to a specific energy, and only specific energies are permitted for the electrons in the hydrogen atom. So that's the first tenet of the Bohr model. Next, an electron in a permitted orbit is in an allowed energy state. If an electron is in an allowed energy state, it will not radiate energy. And because it doesn't radiate energy, it will not spiral into the nucleus. So it'll stay where it's supposed to stay. And then when energy is emitted or absorbed by an electron, it only does so if it can change the electron from one allowed energy state to another. And is going to be emitted or absorbed as a photon with this energy, E equals Planck's constant times by frequency. And he got this from the line spectra. So the line spectra was kind of the starting block for his hydrogen atom theory. So our orbits within here, our energy orbits, where the electrons are allowed, have energy values. So the energies for the allowed energy orbits in the hydrogen atom are given by the following equation. Energy is equal to negative Hc RH 1 over n squared. Okay, so this is Planck's constant. H, c is our speed of light. Our h is our Rydberg constant, and we can multiply all those together to get energy is equal to negative 2.18 times 10 to the negative 18 joules, 1 over n squared, where n equals any integer value. So 1, 2, 3, 4, on to infinity. Okay. And this n value gives the energy of the electron. Okay. And it's become known as the principal quantum number. As a note, this equation only works for hydrogen, right? It will not work for any other atom. And the reason it doesn't work for any other atom is because every other atom are considered, besides hydrogen, are considered multi-electron atoms. So they will not work the same way as an atom that only has one electron. So we're looking at the allowed energy values for one electron and the energy states that they can go to, which are those energy values, n equals 1, 2, 3, and 4. But it's a good place to start when understanding what's going on within an atom. So our energy levels are shown over here on the left, where we've got our principal quantum numbers, n equals 1, 2, 3, 4, 5, 6, on until we reach infinity. Okay? The energy itself is going to increase differently between our different levels. So the difference in energy between our n equals 1 and n equals 2 states is significant. And it decreases as we go from n equals 2 to n equals 3, and then n equals 3 to n equals 4, n equals 4 to 5, so on and so forth. So the difference between the energy levels decreases as we get to a larger n value. Okay? So our delta energy between n values decreases as n increases. Okay? So if we think back to our staircase that we were talking about, this first step would be huge, and then the second step, and it gets smaller and smaller as we go up and up and up and up. So to go from an n equals 1 state to an n equals 2 state, a lot of energy needs to be inputted for that electron to transition from the n equals 1 to n equals 2, and then less so as we go from n equals 2 to n equals 3, even less from n equals 3 to n equals 4, so on and so forth. But again, if we're talking about hydrogen, it only has one electron, and that electron will be in the n equals 1 state because you're going to want to have your electrons in your lowest energy state possible. So the 1 electron in hydrogen will be in the n equals 1 energy level. This is the lowest energy level, and we call this the ground state. So the lowest energy level that an electron can occupy is its ground state. Okay? Anytime we move an electron from a lower energy state to a higher energy state, we say that that electron is now in an excited state. So if an electron is excited from a lower energy state, our ground state, to a higher energy state, it is now in an excited state. So you add energy into that electron, photon hits the electron, transfers that energy to the electron. That electron gets enough energy to go into a higher energy state. It gets excited, and it goes from a lower energy state up into a higher energy state. Ground state is the lowest energy level for an electron. Our energy level is our N value. And then our excited state is any other energy value. So if it gets to any other energy level, and it can only go up, right? You can't go down. You can't go from a ground state to a lower state. You're going to have to go to a higher state. So going from a ground state to a higher state, or just to a higher state, you are now into an excited state. Okay, so any N value that's greater. Okay, and we have terms for this. So we have the term absorption, which is describing the electron absorbing energy from a photon, causing electron to go from a ground state to an excited state. So the transfer of energy from a photon to an electron. It could also be heat. Heat can also cause this. So when it absorbs that energy, the electron goes into an excited state. Okay, so when we absorb the energy and an electron goes from a ground state to an excited state, or an electron becomes excited, being promoted to a higher energy level, we call this absorption. We also have emission, where emission is when we relax back down and release a photon or phonon. In this case, an excited electron returns to a lower energy level, releasing a photon of light or a phonon of heat. So it can release that heat, or it could release that energy as heat or light. And we can look at this when we think about a light bulb. So a light bulb has this excitation process and then return to ground state. So with a traditional light bulb, an incandescent light bulb, heat is used to go from a ground state into an excited state. And then as it goes down from a excited state back down to a ground state, light is emitted. Now, if you've ever touched a light bulb, you know that heat is also emitted. So light and heat are emitted if you have an incandescent light bulb. You could also have LED lights, which are going to be much more efficient. And in this case, we go from a ground state to an excited state. And then once it's in that excited state, it's much more efficient about going back down to the ground state and transferring into light versus heat, which is why if you touch a LED light bulb versus an incandescent light bulb, it is a lot less hot because it's more efficient at turning energy into light versus an incandescent bulb. Okay. So let's actually look at this energy process. So the energy absorbed or emitted by an electron in an atom of hydrogen is given by the following equation. So we're just going to take the equation we looked at earlier and do a change. So our delta E is our E final minus E initial. So using that equation we just looked at a minute ago to look at the orbital energies themselves, we can put those into here, and what we get is negative 2.18 times 10 to the negative 18 joules times by 1 over n final squared minus 1 over n initial squared. Now the nice thing about this equation is it doesn't matter if n final or n initial is larger, it just is going to be describing what's going on. So in an absorption process, our n final is going to be the excited state, and initial is a ground state. All right, initial is the ground state. So n final will be greater than n initial. And when we put this into the equation, this will result in a delta E that is positive, an absorption of energy, which is why delta E is positive. In an emission process, we're going to have the opposite, right? Our n final is going to be ground state. Our n initial is going to be excited state. So our n initial is going to be the greater value, and our delta E will be negative as a consequence, which again should make sense because we are emitting energy, and that is a negative value. So let's look at calculating these out. We've got the following transitions in a hydrogen atom, n equals 2 to n equals 1. So we're just going to put this into our equation. Delta E is equal to negative 2.18 times 10 to the negative 18 joules times by 1 over 1 squared minus 1 over 2 squared. And when we calculate this out, we get a negative 1.64 times 10 to the negative 18 joules. We're going from a higher energy state to a lower energy state, so this is emission, so we would expect a negative value. Okay, next one, we're going from a lower energy state to a higher energy state, so this is going to be absorption, and we should expect a positive value. So let's do this. Delta E is equal to negative 2.18 times 10 to the negative 18 joules, 1 over 3 squared minus 1 over 2 squared gives us a value of 3.03 times 10 to the negative 19 joules. And that's what we get, a positive value. So we see that this is an absorption process. And then if we do the opposite, delta E is equal to negative 2.18 times 10 to the negative 18 joules, 1 over 2 squared minus 1 over 3 squared. We get a negative 3.03 times 10 to the negative 19 joules, which should be expected. The amount of energy that is absorbed will be equal to the amount of energy that is emitted as long as we have a pure absorption emission. We don't have any loss of energy in any other way. So we would just expect that the absorption process will be the positive of the emission process. Okay, there are a couple of limitations with our Bohr model, including it can't explain the spectra of other atoms. So it's very limited to just hydrogen. Only works for hydrogen. Okay, and then it only views electrons as particles. So it doesn't look at them as a wave. So ignores wave properties of electrons. Okay. And because of this, it doesn't really explain why the electron doesn't just spiral into the nucleus. It just kind of glosses over that. It's just like, oh, it doesn't radiate energy. Right? We know that the electron likes the proton, so why won't they just come together? Bohr model doesn't really explain that. Okay, so important things, however, that we can take away from the Bohr's model. Important takeaways is, of course, the idea of those discrete energy levels. So electrons are in discrete energy levels described by the principal quantum number. This is a very important takeaway from the Bohr model, the most important takeaway from the Bohr model. And then the idea that energy is involved in the transition of electrons from one energy state or energy level to another. Okay, and that this transition requires a minimum amount of energy. Okay, that is everything for the Bohr model. I'll talk to you guys in the next video. Bye.